We present a novel semantic labeling method for RGBD indoor static scenes. Our method achieves state-of-the-art results on the NYU depth dataset. The motivation of our work is to discover if hierarchical segmentation can be used to train a classifier to do dense semantic labeling. For robots to truly understand and manipulate their environment, they must be aware of everything in it. You can see in the image some of what we hope to achieve. We test the method by doing two tests, one general labeling, where everything is either the floor, structure, furniture, or objects, and one where we learn the 14 most prevalent classes. We modify an existing hierarchical superpixel-based segmentation method to include surface normals using a modification of Felsenswab and Huttenlocher's method. The edge weight between each voxel is the max of the difference in surface normals and the difference in color, a nonlinear measurement. We then over-segment, construct a hierarchy, and train a random forest with general feature vectors like shape and color histograms. Here you can see a feature learning experiment on a validation set, where we trained a binary random forest classifier on each individual feature for the most prevalent classes to test performance. The results are shown for the top 10 classes, where each column is a feature from a subset of our features, and each row is a class. This shows how powerful simple features can be given good segmentation. This method yields surprisingly good results, as shown by the confusion matrix comparison below. The leftmost is the original method from the NYU depth dataset, showing the 4 general classes. The middle is our method with a bag of words of SIFT features, and the right is our method without SIFT. Below is the confusion matrix for the top 14 classes with our method. This slide shows a table of our method versus other state-of-the-art methods as a comparison. As you can see, we outperform in many categories and have a higher total class accuracy. Here are some visual results of our method on the 4-class generalization. The top row is the RGB image, the middle is the ground truth, and the third is our approximation repeated. Green represents structure, blue floor, orange furniture, and red objects. As you can see, we perform close to ground truth in many scenes, even with difficult scenarios like texture on the bed and bed pillows matching. Here are some visual results of our method on the 14 most prevalent classes as labeled below. This is a much harder task, and although we have low accuracy for many objects, the ground truth and our approximation are still very close.